Using cutting-edge 3D visualization, we explore the architecture of the Central Helvetic Fault and Thrust Belt, its structure, thrusting styles, and lateral relationship, uncovering new geological insight along the way. Located in the Central Alps, this thrust belt records the complex history of sedimentary rocks deformation under intense tectonic forces. During the Alpine orogeny, in response to the collision of the Adriatic-European plate, the kilometer-thick Helvetic rock pile was detached from its substratum and thrust 30 km northwards when the Gotthard Massif was pushed onto the R Massif. The Helvetic sediments were thrust over the R Massif onto the North Helvetic Flysch along a rather flat, narrow surface pushed up in the south in response to the R Massif uplift. The Central Helvetic Fault and Thrust Belt are built by sedimentary rock that record the Mesozoic rifting and drifting of the Tethys Ocean, the formation of an extensive carbonate platform, and the impact of the Alpine orogeny. In the early Triassic, the shift from a continental environment to shallow marine conditions occurred during rifting. By the Jurassic, the rocks of the Central Helvetic Alps captured the dynamic process of rifting and marine transgressions linked to the opening of the Tethys Ocean. During the Cretaceous, carbonate platforms and deeper marine environments developed. During the late Cretaceous and Tertiary, large foreland basins formed and deepened progressively in response to advancing nappes. Early Jurassic, rifting created a block-folded continental margin with marine sediment deposited in graben structures. Middle Jurassic, the region evolved into a passive continental margin where pyroclastic limestone formed in shallow to open marine settings. Late Jurassic, a fully developed ocean basin emerged characterized by massive micritic limestone transitioning into thick marl sequence. During the Cretaceous, carbonate platforms and deeper marine environments developed. Limestone, marls and glauconitic sandstone reveal the interplay of sea level changes and shift of depositional environments that shaped the development of the Cretaceous carbonate platform. During the late Cretaceous and Tertiary, large foreland basins formed and deepened progressively in response to advancing nappes. A foreland bulge formed, was subjected to erosion and eventually submerged by rising seas. Shallow marine tertiary clastics gave way to deep water fleece sediments. Join us on a virtual tour through the Helvetic Fault Belt shaped by two nappes that deformed disharmonically as they were detached, compressed and pushed 30 km north. The belt plunges gently westward at approximately 4 degrees, exposing progressively higher thrust units at the surface. The higher the units, the further south they were before being displaced northward. The Helvetic thrust, an impressive geological feature, where a several kilometer thick stack of Helvetic rocks was pushed over large distances and deformed into a fault stack on its way. North of Mount Titlis, this displacement zone is beautifully exposed. Here, Tertiary Flysch, rich in thick turbidite sandstone, is overthrust by Middle Jurassic Quinton limestone along a knife-sharp fault. The thrust displays intense deformation, including shear zones, meter-sized Boudinot structure, all highlighting the immense compressional and shearing forces at work. The newly defined Schwarzhorn-Balfris zone splits the Central Helvetic Fault and Thrust Belt into two distinct tectonic units. Unlike the sharp, narrow Helvetic thrust, the Schwarzhorn shear zone is broader, up to 100 meters thick, featuring complex faults, thrust, sliver and shear planes. The displacement zone developed from a ramping double fault. The overlying thrust sheet split further into a Jurassic thrust fault stack and a Cretaceous slab that detached and moved independently onto the Balfris shale zone. The entire structure we call the Drusberg nappe. The Jurassic part consists of several stockworks composed of recumbent thrust faults. Erosional remnants of that Jurassic part are seen in the southeast, also called Klippen, shaping spectacularly the red peaks of some mountains, named the Roadstock. Here the red-brown sediments represent Lower Jurassic graben fills, thrust over the Upper Jurassic white carbonate platform carbonates. Cretaceous part of the Drusberg nappe detached from its Jurassic substratum and was pushed over the thick pulvery shale zone, where we see large, somewhat isolated thrust blocks of Upper Jurassic limestone. The Axen nappe can be studied exceptionally well in several transects. It directly overlies the Helvetic thrust, and the structural relationship between Jurassic structures and the frontal Cretaceous structures to the south of the steeply dipping pulverized shale zone can be clearly seen. A key feature is the Cretaceous section, folded into an overturned syncline beneath a major thrust zone. The overthrusted part comprises a stack of recumbent thrust faults of Jurassic sediments. Notable examples include the Rimstock and the Brunistock fault, seen prominently in this region. A striking feature is the overturned Cretaceous melange, sandwiched between the Cretaceous and the Jurassic units. This formation appears as a shared-out limb of an anticlinorium extending westward beneath the Jurassic recumbent folds. Cretaceous front, the melange and the Jurassic recumbent thrust fault stack is revealed in remarkable detail through natural outcrops, Nagravel bores and the Engelberger railway tunnel, offering exceptional insight. To close our video, we present an example of the observed structures, letting the geology speak for itself. First, we visit tight isoclinal thrust faults and synclines, highly compressed recumbent structure with parallel limbs and overturned axial planes, shaped by intense horizontal forces. Shear zones separating stacks of thrust faults reveal complex structure in up to 100 meters thick zones. Hard layers fractured into stacked slabs, while softer mold formed ductile along multiple horizontal shear plane, creating chevron faults through flexural slip. Next, some examples of ramp thrust folding. Here stiff Upper Jurassic limestone detached from its shale base, ramping up into a thrust fold stack as it was pushed northward. The detached northwards moving slab folded into a stunning network of recumbent thrust faults. Let's fly through it in virtual reality to get an impression on lateral changes and dimensions. Two thrusting phases formed a triple repetition of steeply north-dipping Cretaceous strata. A spectacular stack of Cretaceous thrust faults shaped according to our model initially by in-sequence thrusting. A later phase of out-of-sequence thrusting formed the now steep, north-dipping Cretaceous ridges. Eastward stacking pattern oblique to the dominant northward transport direction is suggested by the arrangement of 3 large Jurassic thrust sheets. This arrangement likely reflects the upthrusting of Helvetic sediments along inherited rift graben faults oriented obliquely to the transport axis. The west to east stepping distribution of lower Jurassic rift graben deposits further supports this interpretation. For more details on the Helvetic Fold and Thrust Belt, check out the videos linked in the description below. Thank you for watching. If you found this video informative and enjoyable, please give it a thumbs up and subscribe to my channel for more geological content.